So should I start? Okay, good. Yeah, all right. So let me start. The title of the talk is, as Girish mentioned, is lower bounds for iterated matrix product. And so this is joint work with Hervé Fournier, Nutan Limai, who's in the audience, and Guillaume Malo. Okay. All right. So what's the setting that we are working in? So just to recall, we've seen this result many times already over the past few days as workshop, so I'll just be brief here. So there is a long line of works that that shows that arbitrary but small arithmetic circuits can be simulated non-trivially by small depth arithmetic circuits. So let me just state one of the results, the one that's been discussed the most in this regard in both Neeraj's survey and in Ankit's talk on Friday. So the result of this sequence of papers. So what do we know from all this? What we know is that given any polynomial P in some multivariate polynomial ring, computable by size S, let's say size S arithmetic circuits, and let me also assume that P is of degree D. So P, given any P of degree D, computable by size S arithmetic circuits, P has a sigma pi homogeneous circuit of size okay. So if you start off with a polynomial sized arithmetic circuit for a degree D polynomial, you end up with a sigma pi homogeneous arithmetic circuit of size n to the order square root D. Okay, and what's more, you can say a little bit more about this arithmetic circuit. You can also bound the fan-ins of these pi gates. So you can make these, so if you stare at the proof, so Ankit did this for the determinant, so he got square root n's here, but I'm doing this for a degree D polynomial, so I'm putting in square root D. So you get square root D, and then okay. Yeah. Right. And so this is a very nice line of work, but what makes it more exciting is that now we now have lower bounds for these kinds of circuit. Well, let me just say sigma pi circuits. Yeah. Okay. And of course it's unstated here, but we have the right fan-ins. And the first big breakthrough work in this regard was the result that Ankit presented the other day, where he showed an exponential in square root n lower bound for, well, he talked about the permanent, but the proof that he mentioned also goes through for the determinant. Yeah. So for these two polynomials, we have exponential in square root n bounds. Okay, so this is pretty good. So if you look at, for example, P is the permanent, we want to prove lower bounds for the permanent. What we know is that it has, if it has polynomial size arithmetic circuits, it has depth 4 arithmetic circuits of size n to the order square root n. What we know is that it requires 2 to the size order square root n sized arithmetic circuits of this form. And now the question is, okay, can you improve the lower bound a little bit? Yeah. Can you actually come up with a super polynomial sized lower bound for general arithmetic circuits for the permanent? So there are two ways one could go about this. So two ways possibly to improve this. So the first is, of course, improve this lower bound. So and the second is to improve depth reduction. Yeah. So can you in fact show a better depth reduction from polynomial size circuits to depth 4 arithmetic circuits, right? And an improved depth reduction, well, you can't improve it too much because this lower bound holds determinant as well. But we are only talking about super polynomial bounds here. So n to the order square root n, 2 to the order square root n, there's still enough space to prove a super polynomial lower bound. So can you just improve this a little bit and maybe make your task of proving super polynomial circuit lower bounds easier? Okay.
Exponential in square root n is already super polynomial.
No, but I want to prove super polynomial lower bounds for general arithmetic circuits. So good, yeah, super polynomial. Not for depth 4 circuits in particular. Yeah. Okay, right? And for there all we know is if you have a polynomial sized arithmetic circuit, then you have a depth 4 homogeneous arithmetic circuit of size s to the order square root d. So for the permanent it's n to the order square root n. Yeah. So now if you could improve this n to the order square root n to something closer to 2 to the order square root n, maybe that makes our task of proving super polynomial circuit lower bounds that much easier. Okay. Yeah, and so the main thrust of the result that I'm going to present today is that 2 is not really possible. Okay, you cannot improve depth reduction, well, at least not in the sense of an improved size lower bound for these bounded fan-in depth 4 circuits. Okay, so formally what does it say? So there is a polynomial P in VP, right? So it's a polynomial that has polynomial sized arithmetic circuits. Let's say I'm going to always consider homogeneous polynomials and degree D. Let's say on n variables such that any sigma pi with the right fan-in bound. So let me put in, let me just be a little careful here. With these fan-in bounds, so any circuit computing P must have large size. Yeah. So must have size, in fact you can say something stronger, must have top fan-in s to the, I'm sorry, let me say it again, not s but n to the omega square root t. Okay. Yeah. That's right. So in fact the result is slightly more general. So let me also state that more general fact. If we change the fan-in bounds here a little bit, if we make this sigma pi d, sigma pi t, yeah, so it's a sum of products of degree t polynomials, yeah, with fan-ins of d many degree t polynomials, then you get a lower bound of n to the omega d by t, as long as this capital D is not too large. Let's say this will do. Okay. Alright, so note that this is just this result with t being square root d. So, okay. So, any questions about the statement of this theorem? So let me also talk about what polynomial we are going to prove this lower bound for. So the polynomial, what is this polynomial P? So it's actually a pretty reasonable candidate for lower bounds. So it's the so-called iterated matrix multiplication polynomial. Yeah, and I'll just say IMM from now on. So what is this polynomial? We've seen it already a couple of times, but let me define it again. So you have something like, let's say, x1 to xd, d n by n matrices. Okay, and what this polynomial does is it computes the product. So these are all matrices with distinct variables. I know x1, x2, x3, all the way to xd. And this polynomial just computes the product of all these matrices on distinct variables. Okay, right? So, but strictly speaking, this is not exactly what we want. We want a single polynomial. This gives you n squared many polynomials. So what you do is consider, say, the 1/1th entry of this matrix or something. Okay. Well, if you think about it, if you're looking at the 1/1th entry of this matrix, this is just like you just take the first row of x1, the first column of xd, and it's that matrix product. So for me, this polynomial is just you take a row vector, multiply it with a bunch of a bunch of matrices, and then end up with a column vector. Okay, so that's this polynomial, right? But so this is the formal. This is what the polynomial is, but let's just write down an expression for it just to get a little more familiar with it. Yeah. Right. So for me again, this is a row vector. This is a column vector. And the other intermediate matrices are just, well, the other intermediate variables are matrices, fat matrices. Okay, so what is this polynomial? Well, what am I going to do? It is going to be a large sum, right? So if I want to multiply these matrices out, I take some entry in this matrix, let's say, I don't know, the j1th entry in this row vector. Then I multiply it with some entry here, which has to be in the j1th row. So I take x, j1, j2 in the second matrix. Then x, j2, j3 in the third matrix, and so on until in the final thing you take this and you sum over all choice of all these indices. Okay, so that's the polynomial, right? This is not a very insightful way of writing it down, but that's what it is. Okay, but I also want to write down a different, more pictorial way of looking at this polynomial, and because that's much more useful for us. So I'm sure everybody is convinced that this polynomial is in VP because you can multiply d matrices in polynomial in nd time, right? But nevertheless, let's write down an arithmetic circuit for it. In fact, we'll write down an ABP. Right? So we've been looking at ABPs. Let's write down an ABP for this polynomial. So what does the ABP look like? So recall again, ABPs, you start at a source node. I'll call my source node A. You end at a sink node, which I'll call B, and then you have this kind of directed acyclic graph in the middle, which I'll draw like this. And the directed acyclic graph, so this one computes a polynomial of degree d, so it will turn out that this is a directed acyclic graph where every path from A to B is of length d. Right? So this is the width of this thing. And in between you have layers of vertices. How many layers? Well, something like d minus 1 layers of vertices. Okay, you have d minus 1 layers of n vertices each, right? And now so let's say starting from A you have n vertices here, so you have all possible edges from A to these n vertices, and in general in between any pair of layers you have all possible edges. Okay, so all edges. And now I just need to tell you the weight of each edge, because that's what defines the ABP. Each edge, recall, carries some sort of polynomial weight, usually a linear, a variable or a constant in Amir's definition, but I'm just going to put a variable here. So from the vertex A, for example, to the j1th vertex here, so let's say uj1, I'll just put in the weight x j1 1. Yeah. So the corresponding entry from the row vector x1. Yeah. So that's the weight of the edge going from A to the j1th vertex in this layer. In general, if I take a couple of layers in the middle here, let's say this is the ith layer, right? And I take maybe the j I minus 1th vertex here and the j ith vertex here, and I look at this edge. Well, the weight of this is going to be x ji minus 1 ji, and this is the variable that comes from the ith matrix. Okay, right? So I've just taken the variables that define the iterated matrix product and put them in this ABP. Yeah, let's just verify that this ABP computes the polynomial we've written down. Okay, so recall what the definition of the polynomial computed by this ABP is. Well, what do? I take all paths gamma. So gamma is a path from A to B, and I compute f gamma, which is the product of all the variables that you encounter along gamma. Let me just say product here. Product of variables are encountered along gamma, and then the final polynomial is f, which is just sum f gamma. Okay, so in this case, if I choosing a path from A to B is choosing a j1th vertex to go to here, then a j2th vertex to go to here, etc., etc., etc. Yeah, and if I do that, you will see that the weight is, let's say, to go to a j1th vertex I get weight this, to go from the j1 to the j2th vertex on the next layer I get weight this, etc., 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 and I get maybe d minus 1. Okay, so that's the weight of the path gamma specified by these vertices, right? So if I sum this up, then I get exactly a definition of IMM, and hence that's exactly what this ABP computes. Okay, right? So actually we haven't really done anything. If you look at this ABP, it's actually very, I mean, I've labeled the variables in some way, but all this is kind of a very generic ABP. So I've taken an ABP, just a generic graph with all possible edges of width n, so to speak, right? There are n vertices in each layer, so width is n, and I've put different variables along every edge. Every edge appears exactly, every variable appears on exactly one edge, right? So in a sense, this is the generic ABP. Yeah, it's the most generic ABP you can find. So you can take any ABP and kind of reduce it to this one, right? Because this has different variables along anything, so this is in some sense the hardest ABP. Yeah, so that's one of our motivations for studying this polynomial IMM. So one is that, so two properties of IMM I would like to write down now. So one is that it's hard for this very hard and, well, it's complete really. It's complete for this ABP model of computation. kind of the polynomial computed by the most general ABP, so it's kind of complete for ABPs. Yeah. And another is that if I stare at the definition of iterated matrix product, just stare at it for a second, and for a second think that these variables, the various variables defining it, take only 0, 1 values. So when they take only 0, 1 values, what you're really doing is taking this directed acyclic graph, throwing away some edges, keeping some others, and now there are no weights. Right? The ones that have weight 1, those edges stay. The ones that have weight 0, those edges are deleted. And so just a 0, 1 setting to all those variables defines some sort of directed acyclic graph in this template. Right? And now what this polynomial does is it counts the number of paths between A and B. Yeah. So you can see that this polynomial, therefore this polynomial and its evaluation is fairly closely related to things like small complexity classes like log space, non-deterministic log space, and so on, where counting number of paths is kind of the natural complete problem. Okay, so there are connections to non-deterministic log space and other classes. Okay, fairly natural connections. Okay, so these are two reasons to study the iterated matrix product. Okay, and this is the polynomial for which we prove this lower bound. Okay, so we have one more result that I'd like to briefly state before I go on to proofs, and this is about set multilinear formulas. Okay, so as I said, we take this polynomial IMM and we prove that lower bound for it, the lower bound stated in Theorem One. It turns out, however, that the lower bound is also tight. So that's an interesting fact, that the lower bound in Theorem One is actually tight. Okay, right? So we already know it's tight for square root d, right? Because that's what all this Tavener stuff is about. We know that there are polynomials depth 4 circuits of that form of size n to the square root d. So there it's of course tight, but it's in fact tight for any parameter t. So it's tight in this setting as well. Okay, so if you want to write it as a sum of product of degree t polynomials, then the top fan-in can be made something like n to the order d by t, and this holds for any t. Okay. Yeah. And how does one see this? Well, you could just go back to Tavener and argue it out, I guess, but there's a much easier way of seeing it for this polynomial, and this is much older than I guess any depth reduction result. This is just a generalization of what we call Savage's theorem, right? So what I want to claim is that this polynomial IMM that I've just defined, and I'm going to just use this picture from now on. So this picture does have sigma pi circuits where the bottom fan-in is bounded by t, yeah, of size n to the order d by t. And by size now I just mean the top fan-in. Yeah, that's my size for now, the top fan-in. Okay, so how do I do this? Well, as I said, this is just a generalization of Savage's theorem, and you just do what you do there. So you just break this up, break up this picture into segments of length t. Okay, you have all these segments of length t. Okay, and how many segments are there? Well, there's something like d by t segments. So these are d by t, many of them, approximately. Okay, and so now what you do is, well, you kind of do this by kind of simple divide and conquer. So let me just introduce a little bit of notation. So given two nodes u and v in the ABP, I'm going to kind of look at the ABP in between u and v, just the directed acyclic graph where I just keep the nodes in between these layers, so to speak, right? And PUV will be the polynomial computed between u and v. so to speak. Yeah. So sorry, this picture is not really accurate because I have all edges going out from U and all edges going out from V. But let's say I keep all this stuff and all this stuff. Okay, so I keep that segment of the ABP, throw away the rest. And now this is a sub ABP. The source node is U, the sink node is V. And so now I can talk about the polynomial computed from U to V, between U and V. Yeah. And this polynomial I denote PUV, right? And PAB is just the IMM. Yeah. I don't know if I'm using subscript, so good. It's IMM ND. Okay. And if you really think about it, PUV is kind of IMM but on a smaller number of matrices. It's the same kind of. Okay. So anyway, how does one come up with this generalization of Savage? Well, what one does is that we run over all possible choices of vertices in each of these layers. So let's say this is the I1th layer. So the vertices here, let me call them, let's say, I don't know, C11 to C1n, and similarly in the second layer C21 to C2n, etc. And this one is the d by tth layer, so it's C d by t n up here. I'm sorry. Oh, sorry. C n d by t, C1 d by t. Okay, good. Yeah. So now I have all these labeling. So what I do?
What are their vertices?
Yeah, they're just the vertices on these layers. Yeah, just all the sets of vertices on these layers. So now what I do is I take all the paths going from A to B and I group them based on the set of vertices on these special marked layers that they go through, right? So every path from A to B is going to go through exactly one vertex in this layer, one vertex in this layer, etc., etc., etc. Yeah. So I can write PAB as the sum, right, for every choice of let's say CI11 to CI d by t d by t. Yeah, for every choice of vertices on all these marked layers, I just look at the sum of the paths that pass through the vertex CI11, CI22, etc., etc., etc. Yeah. Now if I'm looking at paths that pass through all these vertices, it's fairly easy to see that the polynomial I'm computing is really this polynomial. Right. So a polynomial between the paths that go from A through CI11, if I just take the segment, the first segment of all these paths, then I get the polynomial PACI11, and similarly the second segment is going to give me this polynomial, etc. So this is just the sum of products of all these. Okay, and that's it. Now you just expand each of these, expand brute force as a sum of monomials, and you have your depth force circuit, right? So that's the construction. So you write it as a sum of products, expand each of these terms of products again as a sum of products, and you have your sigma pi circuit. What are the degrees of these polynomials? Well, the degrees of these polynomials are the lengths of these segments, so that's t. Okay? So these are in fact exactly degree t polynomials. Okay, so degree, say PACI11 is equal to t, and in fact the same for all of these. What's the top fan-in of this circuit? So recall that the top fan-in is the size, the fan-in of the sigma gate up here. Well, the fan-in of the sigma gate is the number of choices for these vertices, so there are n choices for each of these CIs, so the top fan-in is something like n to the d by t. Yeah. And what about the overall size of the circuit? That's also an interesting parameter to track. The overall size of this circuit, well, it's governed by two things. First of all, the product gates in this circuit are really small if you look at it. So this is a product of d by t, guys, so that's polynomial. And when you expand it out on the inside, that's a product of t, guys, that's also polynomial. So the product gates are never big. What are big are the sum gates. So the size of this circuit is really governed by the maximum fan-ins of these sum gates. So the sum inside when you expand this out, and this sum gate here. So the size is really governed by the maximum of n to the d by t, and when you expand out the thing on the inside, you'll get n to the t. Okay, and now if you want to minimize this, so minimize by t equals square root d, you get, well, you get Tavenas in some sense. Okay, good. Right, but yeah, this is much older than that. Okay, good. So, but I want to note something more about this sigma pi circuit that we constructed. It has what I was referring to as the set multilinear property. Yeah, it's in fact a set multilinear depth 4 formula. So what does set multilinear mean? I'm just going to define it using this example. You can generalize the definition. So if you stare at IMM, well, it has the following two properties. It's homogeneous, right, and it never multiplies variables from the same matrix. Yeah, you fix a matrix xi, it never multiplies two variables from the same matrix. It doesn't help. I mean, when you're computing matrix product, for example, if you look at a path from A to B, that never multiplies two variables from the same matrix, from the same layer. Can't happen, right? So IMM never does this. And a set multilinear formula intuitively is things that have this property. Yeah. So if you look at the circuit that we constructed up here, the depth 4 circuit, well, each of these, for example, PACI1, the polynomial corresponding to the first segment, it looks at the matrices x1 through xi1 or something. Yeah, x1 through, well, yeah, x1 through xt. Yeah, and then it just essentially computes an iterative matrix product on those matrices. So it never has to multiply two variables from the same matrix. Yeah, so each of these polynomials by themselves is set multilinear. And moreover, distinct polynomials really just compute polynomials on different matrices. So again, you're never multiplying two variables from the same matrix. Yeah, so this is really a refinement of multilinearity. In multilinear circuit formulas, you never multiply two variables. Well, you never multiply a variable with itself. Here you never even multiply two variables from the same matrix. So it's a refinement of this notion. Right? So this is what I call a set multilinear formula. Yeah, so this property, if this property is satisfied in the formula that we construct, that is set multilinear. Okay? And the formula we constructed above is definitely set multilinear. Okay, so set multilinear formulas are a very nice restriction further of multilinear formulas to look at. In particular, it's known by a very nice result of Raz that if IMM has polynomial sized formulas at all for small d, reasonably small, then in fact it has polynomial sized set multilinear formulas. Okay, so in some sense, if you want to prove lower bounds for this polynomial, it's sufficient to look at set multilinear formulas. Okay, so it's a nice interesting model to look at. So well, what we can show is that any set multilinear sigma pi formula must have now not top fan-in but size okay, must have size n to the omega square root d. Okay, so note the difference between theorem 1 and theorem 2. So theorem 1 is in some sense a stronger model because you don't enforce this you don't enforce set multilinearity. You don't even strictly enforce homogeneity except for these fan-in bounds, right? So here you enforce both homogeneity and set multilinearity, but on the other hand here you don't enforce fan-in bounds. Yeah, so the polynomials at the bottom could be huge, the multiplication gates could be computing huge degree polynomials, you don't care. Okay, And in some sense here, you cannot obtain a top Fanon bound. You must obtain a size bound, right? Because these polynomials at the bottom could be arbitrary degree polynomials. And if you only talk about top Fanon, well, this part could just compute your entire polynomial for you. So you can't really get a top Fanon bound here. You must aim for a size bound, and in fact you can get the right size bound. Okay. So let me also mention some previous work in this regard. So of course we build upon this result of Nissan and Wigderson that introduced the partial derivative method to arithmetic circuits. And so they were in fact the first people to consider this polynomial for the purpose of arithmetic circuits, as far as I know. So they prove a lower bound of 2 to the omega square root d, yeah, for sigma pi set multilinear. In the same model, they prove a lower bound of 2 to the omega square root d, and but they also have a more general result. So they get 2 to the d to the 1 over r for something like depth 2r. Okay, so there are more general results, exponential lower bounds even for set multilinear constant depth formulas just for this polynomial. Yeah. So the only advantage here is that it's a tight result, but also philosophically you want n to appear here. I mean this is a lower bound that works in fact for all n, but it's a lower bound that doesn't depend on n. Yeah, you think the polynomial gets harder as n gets bigger, and in fact that's kind of the difference between ABPs and formulas. Constant width branching programs are like formulas, large width branching programs, well, they are ABPs, and you think that they are different. So you want n to kind of show up in this lower bound somewhere and to quantify that difference. And this kind of does that for depth 4. Right? If you're just looking for stronger, so there's also a beautiful result of Ran Raz and Ahmed Yehudeov, who give lower bounds even in the more general setting of multilinear formulas. So they have lower bounds of something like exponential in omega again. So I'm just going to say square root n log n. Right? Here n is the number of variables and roughly the degree. So let me just say that we have a lower bound of something like this, right? So Amir will correct me if I'm wrong. So this is here, both n is the number, well, n is like the degree, the number of variables could be n square or n if you're just looking for an explicit polynomial. So there are lower bounds of this much, not just for the set multilinear world, but for even for constant depth. Oh, oops, let me say for multilinear sigma pi. Okay, and again there are extensions to higher constant depths and so on. Okay, so I'm probably going to start going into proofs now. So are there any questions about the statements of either of these theorems? Oh, so is it actually 10:40? Okay, good. Okay. All right. I started 5 minutes late, no?
Yeah.
Okay, good. Yeah, I need that 5 minutes now. All right. Okay. So let's go into the proofs of some of these things. So let me just try to prove theorem 1. So I guess I won't have time for theorem 2 then. So okay, I can just click. All right. So how are we going to prove theorem 1? Well, we are going to use the method that was introduced by Ankit and Neeraj, the shifted partial derivative method. Okay. So just to recall how this goes, so Neeraj in his survey he defined this nice linear map that he called phi sub L. So let me just redefine it here to recall. So suppose you have this polynomial f that you're trying to prove lower bounds for, yeah? Let's say f in fx. You look at the partial derivatives of f of certain degree. So let's say to kf, the set of polynomials p1, p2 to pr. Okay. So phi L is defined as follows. So it takes as input a bunch of polynomials. These are all of degree at most L. And what it outputs is right, so it outputs the sum of all these polynomials. And the complexity measure that we consider is the dimension, well, the rank of phi L. Right, the rank of this linear map. And this is just the dimension of the image of this linear map by simple linear algebra or by definition. Okay, so what's the dimension of this linear map, the image of this linear map? Well, I want to know the size of the space that the image of this spans. So I can just start with the basis here, see what phi L does to this basis, and then take the dimension of that. Yeah. So what's a basis here? So well, what's the input space of phi L? So the input of phi L, if you think about it, is just a cross product of a bunch of vector spaces. It's an R-wise product, and each of these vector spaces are just polynomials of degree at most L. Yeah, and it gives you, it spits out a polynomial. Yeah, so that's what phi L is, right? So now a natural basis for this would be, you start with an arbitrary monomial here and put in 0, 0, 0, 0, 0. Yeah, or start with an arbitrary monomial here, put in 0, 0, 0, 0, etc. So all these elements form a basis for phi L. So now the rank of phi L is going to be essentially the dimension of the span of what phi L does on all these basis vectors. So what does it do on this particular basis vector, for example? It outputs m times the polynomial p1. So in general, this is going to be most L okay, right? And this is exactly what Ankit called the set XL. Okay, so you take the kth order partial derivatives of f and you shift them by monomials of degree at most L, and that's exactly what you get. Yeah.
Do you have to consider all monomials? All monomials?
Yeah, so you want a basis for this space, so you take all monomials of degree at most L in each coordinate. So that's a basis for this space.
We could have just taken one line.
Yeah, that one is also in here, but all monomials of degree at most L. Okay. So so I estimate. So I want to estimate this particular complexity measure for my polynomial. So, but what kind of lower bound do I need on this complexity measure? Well, to understand that, first of all, we have to look at the upper bound of this complexity measure on small circuits. Okay. So let's say C is a sigma pi circuit, say, doesn't matter, circuit of formula, circuit for what can I say about this, the dimension of this span of C, the complexity measure of C. So let's say C is some I, Ti, where each of these Ti's are circuits of this form. They are products of degree T polynomials. Okay. So as Ankit already mentioned, all you need to do is, so I'm going to just abuse notation here and say dimension of C for the complexity measure of C. So the dimension of C, as Ankit mentioned, is just the sum of these dimensions. And let's say there are S many such guys. You have S many terms here. And then now the dimension of each of these guys is what Ankit has already upper bounded for us from the last time. So let me just state that upper bound because I'm slowly running out of time and I don't have time to work it up now. But it's a fairly easy exercise to work out that this is equal to S times, well, it's a funny pair of binomial coefficients. It's n plus L plus KT, choose L plus KT. Okay. So that's the upper bound we kind of need to, this is kind of the upper bound we need to beat to get non-trivial lower bounds for this complexity measure. I'm sorry, to get non-trivial lower size lower bounds via this complexity measure. Okay. So I think I have enough time to lower bound this quantity reasonably formally. Yeah, so how do we lower bound the complexity measure for the polynomial we are interested in? Yeah. So to do that, let's start with a small warm up where we actually just look at the partial derivative space of this polynomial and lower bound that. Yeah, and then we'll get to the shifted partial derivative space. So for now set L equals 0, so I'm not shifting at all. All I'm doing is taking partial derivatives. Yeah. And now I want to lower bound the dimension of this thing. Okay. Yeah. And for now let's say K is a parameter that I can choose at will. So I can choose K to maximize the dimension of this space. And I want to know what the right K is. I'm free to choose K as I like. Okay. So let's just see what the derivatives of this look like. Let's go back to our picture. Right. So now I'm going to take derivatives of this IMM-ND polynomial with respect to a few variables. Well, what are variables? We call that every variable labels an edge. Yeah. So a variable essentially looks like something like, I don't know, X, I, J, P. So it comes from some pth matrix and it's the edge between vertex I and vertex J. Okay. Right. So note that, of course, recall that IMM is this set multilinear polynomial, so it never multiplies variables from the same matrix. So if I take, for example, X and Y in the same matrix and I derive this polynomial with respect to both of these variables, well, what I'm going to get is 0. Right? So it never makes sense to take derivatives with respect to two variables from the same matrix. So you better take derivatives with respect to different variables from different matrices. So let's say I take maybe the I1 J1 variable here, the I2 J2 variable here, the I3 J3 variable here, etc. Well, what's the derivative going to be? So recall that the monomials here are paths going from the source to the sink. So any monomial that does not involve in either any of these variables, even one of these variables, will be set to 0 on taking the right derivative. Right? So the only monomials that survive are paths that go through all these edges. Yeah? Could have multiple such paths, etc. Yeah? From these paths, these edges are deleted and the rest of the path survives. Right? So in general, now I'm going to think of my derivatives as just sequences of edges like this. So just to introduce a little bit of notation. So my derivative is a tuple of numbers like this, I1 J1, I2 J2, etc. This is living in the space n to the 2k if I'm taking k derivatives. Yeah. And the derivative itself is just the sum of all the paths that pass through these edges. I'm not, sorry?
The indices of the layers.
Ah, good. I'm not including that here. Yes, I'm not. Yeah. So we'll fix that eventually, so it won't matter. Okay. Right. Good. So now, let's try to lower bound the partial derivative space of this thing. So first of all, we are never going to take derivatives with respect to two matrices in the same layer. So we have to choose, variables from different things. In particular, you can never take the same variable twice. So the maximum possible space maximum possible number of non-zero derivatives, yeah, is at most n choose d, right? I'm never going to even take the same variable twice, so I can only choose n choose d many derivatives. And what I want to show you is that if you choose k correctly, you can actually get roughly n choose d many derivatives. Okay, you choose k so that that happens. Well, what you do is that you take all the even matrices, for example. So let's take x2, x4, x6, etc. Okay, and now my derivatives are going to be all possible edges, one from each of these matrices. Okay, those are my derivatives. Yeah, so my I1, the I that I'm going to use, the tuple I, these are all possible settings of I, all possible I1 J1 from the matrix x2, I2 J2 from the matrix x4, I3 J3, all the way until I d by 2 J d by 2. Okay. So now let me fix, so I want to analyze this space of derivatives, and I want to show you that these are large. So if I fix this I1 J1, I2 J2 all the way until I d by 2 J d by 2, what do I get? Well, I get the sum of all paths passing through all these edges. Yeah, but if you think about it, there's just one path passing through all these edges, right? Because from here I have to go here, from here I have to go here, etc. Yeah, so the path is completely determined. So the derivative with respect to this is just a monomial. Yeah, so once again, abusing notation, is a monomial. And what's more, the monomials are all distinct, because if I tell you the derivative with respect to one I, then that kind of determines I, because the gaps in the path kind of tell you what the variables were with respect to which you took the derivative. Okay, so if I give you the derivative monomial, it's got a few gaps, but you can fill in the gaps uniquely to get back the variables with respect to which you took derivatives. Right, so you have a bunch of distinct monomials. So therefore the size of this partial derivative space is just the number of monomials you get. Well, they're all distinct, so that's equal to the number of derivatives. And how many derivatives are there? Well, there are d by 2 choices for that you have to make, and each of these can take values from 1 to n. So that's n to the, well, there are d choices, n to the d many derivatives. Okay, so you have n to the d many linearly independent derivatives, and the reason they are easily seen to be linearly independent is because they're all monomials and they're all distinct. Okay, so that's something to keep in mind. All right. So much for the warm up. So how does the entire thing go? So now let's go to shifted partial derivatives. And the only lesson that I'm going to take from this is that I'm going to try to make my derivatives monomials. Okay, so how do I make my derivatives monomials? Well, let's go back to the picture. Okay, so first of all, let me tell you the variables with respect to which I'm going to take derivatives. Now I'm going to take only k derivatives, not d by 2. Okay, I'm going to take k derivatives. It's important that I don't take k to be too large, you'll see. Okay, so now which k derivatives do I take? Well, the most natural thing is to kind of choose k matrices that are well spaced out in the ABP. So let's say the P1th matrix, the P2th matrix, the P3th matrix, etc. Yeah, so these are k matrices that are as well spaced out in the ABP as possible. So what's left in between is the space of size d by k or something. Okay, and now my derivatives are going to be with respect to one edge in each of these matrices. Yeah, so I choose I1 J1 in the first matrix, I2 J2 in the second matrix, IK JK. Okay, so that's my derivative. Alright, so now notice that if I take derivatives with respect to these variables, I no longer get monomials. right? Because I'll get the sum of all paths passing through all these edges, so I'm going to get multiple, etc. Okay, so that's no good. All right, so I don't know how to analyze this. So I want to go back to the case when I have just monomials. Okay, it turns out there's a simple trick, a simple way to do this for the iterative matrix polynomial. Okay, so how do we do this? Well, I'm going to set lots of variables to 0, and that's going to kill most paths. Okay, yeah. Notice that I want to prove a lower bound for iterated matrix polynomial, but if I set a few variables to 0, I only get an easier polynomial. So if I prove a lower bound for an easier polynomial, I still have a lower bound for the harder polynomial. So let me just work with an easier polynomial. And what's this easier polynomial? Well, now I choose matrices in the middle of these segments, right? So I had segments of length k, I'm bisecting them further, so now I have segments of length d by 2k, and let me call these matrices q1, q2, these are the matrices indexed q1, q2, q3, etc. Okay, yeah. And now what am I going to do with these matrices? Well, I'm going to, nothing actually, I'm going to leave these matrices as they are. I'm going to kind of set variables in the other matrices, other than these. Yeah. So what I'm going to do is I'm going to choose now for every layer, let's say between the q1 and the q1 plus 1th matrix, in the q1 plus 1th matrix, I choose a matching from the vertices, n vertices here to the n vertices here. So let's say the identity matching. I leave all these edges as they are, and I kill all the others. Yeah, I just set all the others to 0. Yeah, so those paths no longer exist. The corresponding monomials die out. There are no paths that take those other edges. Similarly in the next layer, etc. Yeah, and this is for all matrices other than the p's and the q's. Okay, so that's the new polynomial. Let me just call this f. Right, they're just deterministic, right? Okay, so that's the matrix. So now recall that in the p's and the q's I have all possibilities still. So I mean, I've not sacrificed that. Okay, so now what happens? Well, let's try to take a derivative and see. Yeah, so now I fix. Again, I'm going to take derivatives only with respect to variables in the p matrices. Yeah, so I take an edge in p1, I take an edge in p2, maybe my p2 guy is here, and p3 is here. Now let's see. So I want to look at all paths from a to b that pass through these edges. Well, suppose I start at a. Recall that I've already chosen a matching. So in this case, matching is just a single edge. Well, there's only one choice. So I go to the next guy. Then there's only one choice further. I go to the next guy, all the way until I go to q1. Right? Yeah, until there's just one choice path. Right? Yeah. But now I have multiple choices. But note that I need to pass through this edge. But now if I want to pass through this edge, I must have come from this guy, etc. I must have come from here. Yeah, which means that in this layer I must take this edge. Yeah, there's only one choice really. Just one choice, take that edge. Okay. Similarly from here, there's just one choice, go here. But now since I want to pass through this edge, I have to come here, so I have to take this edge. Yeah, etc. Right? So now there's just one path through every choice of derivative variables. Okay, so now the derivatives are monomials. Okay, all right, good. So let's estimate the space of partial derivatives. Yeah, the advantage of doing all this is now the estimation of the space of partial derivatives just becomes monomial counting again. Yeah, previously in Ankit's talk he talked about leading monomials and so on. Here that's not really important because the leading monomial is just the monomial. All the derivatives are monomials. When you shift them by monomials, they're still monomials. So all you want to do is count the number of monomials. Yeah. I've fixed f. That's it. F is done. That's all. I'm only going to look at the shifted partial derivative space of f. Yeah. So let's lower bound the dimension of f. Yeah, and this is just the size of all these things. So what do I call it? Here m is a monomial of degree at most L, and I is this kind of weird component. Okay. Yeah. So this is just a set of monomials. All these derivatives are monomials. I'm shifting by monomials. So this is a set of monomials. And let me call this set capital M. The set, the lower bound on the size of capital M will give us a lower bound overall. Oops. Yeah. Okay. So how do I lower bound the size of capital M? Well, it's not very difficult. So I can write M, if you think about it, as a union over all choices of this tuple I of Mi. Yeah. So Mi is all those monomials I get by just shifting the derivative with respect to I. Yeah. So that's a subset of M. So here I have all M and all I. If I just fix an I, the stuff I get I call Mi. Yeah. And I want to lower bound the size of the set. And the most natural thing maybe to do is to do inclusion exclusion here. It's the set of monomials I get by shifting just the derivative with respect to I. Right? I fix an I and then I just vary over M, little m. Okay, I have this, and the advantage of this expression is that the first expression is trivial to evaluate. Okay, so what is the first expression? Yeah, so for any I, if I look at Mi, the size of Mi, yeah, it's the number of different monomials I get by shifting a fixed monomial, the derivative with respect to I, right? And these are all distinct, right? If I shift a monomial by different monomials, I get different monomials. So this is just the number of monomials of degree at most L. Yeah, so this is a fairly standard kind of binomial expression. This is this. So that's trivial to evaluate. What about the other guy? Well, that requires a little more work. What can I say about? Yeah. So how many monomials are shifts of both the derivative with respect to I and the derivative with respect to I prime? Yeah. So you can see that if a monomial is the shift of both these different derivative monomials, then the derivative monomial must divide this monomial, right? So this is just the set of monomials. This is a number of monomials divisible by both. Divisible by both the derivative with respect to I and derivative with respect to I prime, and I'm going to, if its derivative is divisible by both these multilinear monomials, it has to be divisible by their least common multiple or whatever. And if you think about it, it's just the union of the variables in this, right? So I'll just write that as yeah, but it's exactly this set of monomials, right? So if I know this set, this is a multilinear monomial. Once I know this set, yeah, so then the number, this is going to be, so this is going to be, it's going to be a number of monomials of degree at most L plus D minus K, right? Because a derivative is of degree D minus K, the shift is of degree L. So every monomial of degree at most L plus D minus K divisible by this product of monomials. Well, that's exactly my set. Yeah. So once I fix this, so this is just the number of monomials that contains a given monomial. So again, this is the binomial expression of the above form, but the binomial expression is kind of governed by the size of this. Yeah. So if you think about it, this is just n plus L plus D minus K minus the size of this, whatever that is. So let me just say, yeah. Okay, so just that's what it is. Okay, right? And so I'm sorry, it's the union here, the union. Yeah, so if you have now if you have the union of two sets, well, you take one set. So let me just look at this. So this is the size of any derivative, right? So if you take the derivative with respect to an I, you get a monomial of degree d minus k. These are two monomials of degree d minus k, and you're kind of taking their union. So it's going to be a size more than d minus k. Yeah, and it's going to be more than d minus k by the symmetric difference or something, or by the difference of between the one of the two sets from the other. Yeah, so this is just going to be n plus L minus something like, let's say, yeah, so that's the expression. Yeah, it's by here I mean the difference, the number of variables in this derivative that's not in this derivative, number of variables in this derivative that's not in this derivative. Okay, so how large can this be? Recall that we need to upper bound this quantity. So if you now look at this ABP, you'll realize that actually this can be pretty large. Well, how small can this be? Yeah. So if I look at, for example, now I have an I, so recall that I have a unique path going through the variables here. Now let me take an I prime which is different from I, yeah, and I want to kind of upper bound this quantity. So I want to say that I minus I prime is always, the derivatives are always kind of different from each other, and the more different they are, the smaller this quantity is and the better my evaluation, whatever, my estimate. Yeah. So let's say this is I, and my I prime just differs from I the single edge. Yeah. So it just differs at one endpoint. So I is some tuple. So I1 J1 through Ik Jk, and I prime is just I but different at a single spot, just the first. Yeah, it just differs at I in the first place. Yeah. Now if I look at the derivative with respect to I prime, you can see that, well, this path is going to be different because there is just a single path, and well, you will have to change at Q1, but from here on, well, you're just the same. From here on, you're just going to follow this path, etc. So these paths are going to agree on every segment except possibly the first segment. Yeah, that's the only segment where they differ. Yeah, even in the first segment, they're going to agree until, say, the Q1th matrix, and then differ from then on. Yeah, so they'll only differ in a small segment. Yeah, and this segment is of length d over k. Okay, so the two monomials, the two derivatives, they're both monomials, but they agree on all except d over k places. Okay, and in general, if you want to upper bound this expression, the best you can say is n plus L minus d over k, choose L minus d over k. Okay, that's all you can say if you want to upper bound this expression in general. But on the other hand, so if you plug in parameters from here on, I don't have time to work it out, but if you plug in parameters from here on, you're in trouble. You don't get the right lower bound. Okay, and if you think about it, the reason for this is kind of, you're taking a very bad bound here. This L minus d over k, choose L minus d over k, it's a really bad bound because this is a worst case bound on the amount that a pair of derivatives can share. But if you look at a typical pair of derivatives, so a typical pair of derivatives is just a typical pair of tuples like this. They don't differ in exactly one place like this. They in fact differ in order k places. Yeah, because these are actually words in an alphabet of size n of length k. Yeah, if you are looking at an alphabet of size n, well, words are going to differ when n is large, even n is 2 really. Words in typically are going to differ in order k many locations. Yeah, so a typical pair of derivatives will not just differ at one location, but in like order k locations, right? So what we'll do, instead of looking at all derivatives, is to look at a subset of derivatives that form something like a code-like structure, and that's it. So that will complete the lower bound. Okay, so recall again, we are trying to lower bound the size of M. I'm going to lower bound it by not mi for all I, but from a subset, yeah, where C is a subset of n to the 2k such that 1, it's pretty big, let's say it's n to the k, 2, 2 for all distinct tuples in C, the Hamming distance is, let's say, at least k. Okay, and that's it. So now you plug in this into the inclusion exclusion expression, and this is going to be something like n plus L choose L. This is the number size of each of these times n to the k minus n to the 2k times n plus L minus d choose L minus d. Okay. All right. So that's essentially the expression. Okay. So at this point it turns into a slight computation. So you have to fix parameters. K and L are parameters that you can choose now. Yeah. You will see that the right kinds of parameters to choose, if you think about it, there are two governing things here. You want to beat this bound here, n plus L plus kt, choose L plus kt to get a non-trivial size bound. But at the same time, you want this expression to be non-negative, so you want the first term here to beat the second term here. So these, it turns out, are kind of conflicting constraints. Okay, and if you work it out, what you will see is that what you need is something like k equals, let's say, something like d by 2t will work, and the lower bound you get is s greater than or equal to n to the omega k, which is n to the omega d by t. Okay, right. Okay, so let me stop here. Yeah? I'm sorry for going over time. Thank you.
So I don't understand why fixing the matching depends any should there just in principle.
Right. So okay. So it doesn't in some sense. Right. So it doesn't in principle. So so I kind of hid a part of the proof. So you can do it without fixing matchings first of all. So and that's how we initially proved it. But the advantage of fixing this matching is that you're proving a stronger statement, and it helps you to prove theorem 2 that I talked about, the lower bound for set multilinear. And there the problem is that the bottom fan-in is not bounding. And the most natural way to reduce bottom fan-in is to set lots of variables to 0, because then lots of things vanish. Right. So not deterministic. So the thing is, if you get this lower bound for one of them, well, it was irrelevant which matching we chose. So we could choose any one matching in each layer. So I chose the identity matching, but you could choose any matching, different matching. So now if I set everything at random, I get essentially the same polynomial. Right. Okay, good. Absolutely. You're absolutely right. Yeah.
So this says that the lower bounds for like sigma pi sigma does not use general lower bound, because there is this polynomial in VP which.
Right. So it says that sigma pi bounded fan-in does not yield super polynomial lower bounds for general circuits. But yeah, so there are variants you could try, and yeah, so Chandan will talk about something in the next talk where we still don't know. So that's a variant of sigma pi, and we don't know whether lower bounds for that will actually yield super polynomial circuit lower bounds. I mean, it's not clear. Yeah.
But for unbounded fan-in, we know that it does yield.
Unbounded fan-in what?
So there's the star sum of depth for that. What does that do?
Oh right. So that's exactly the result of Tavenas I stated earlier. So that actually gives you bounded fan-in circuits. Yeah. So it's just that. Oh no. So let me rephrase. It says that if you prove a super s to the square root d lower bound, then you get a super polynomial lower bound for general arithmetic circuits. It's just that with this method, the best we can do is s to the order square root d, and we can actually get such a lower bound for even polynomials in BP.